Hello, everyone. Welcome to the webinar. We will begin in a few minutes. Please take a moment to respond to the poll on your screen. How many individuals are attending this webinar at your location? If there are more than 5 people in the room, please enter the number of attendees present in the questions box.
Hello.
Hello, everyone. Welcome to EPA's 17th Annual Drinking Water Workshop. We are glad you could be here virtually with us today for webinar session 5A on Monitoring and Distribution Part 4, Water Quality Changes. If you have not done so already, thank you for your responses to the poll. All right, let's get started. If at any time during the webinar your screen does not load the next presenter's presentation, please try refreshing your browser. If that doesn't work, you can try exiting full screen mode or exiting and rejoining the webinar. We're here to help, so at any time, feel free to use the questions box for any other technical issues. Now, let's hear from Mike Finn, who will introduce our first speaker and help moderate the webinar.
Good afternoon, everyone. Thank you for joining us. Welcome to session 5A, Monitoring and Distribution 4, Water Quality Changes. Our first speaker, let's get started, is Melinda Friedman. Melinda is president of Confluence Engineering located in Seattle, Washington. Melinda has many years of experience, including providing service related to source water and distribution system water quality, evaluations, regulatory compliance, and optimal corrosion control. And with that, Melinda, I'm passing it over to you.
Hey, Melinda, are you able to hear us? I think you might be muted. Hey, Melinda, hang on one second. I think you're muted.
Can you hear me now?
Yes, we can hear you.
Okay, great. Sorry about that. Okay, so we'll be talking about source and treatment changes and impacts on distribution system water quality. Slides to advance too. Okay, so presentation overview, we'll start with background and reasons for concern, corrosion control strategies that can impact changes on distribution system water quality, disinfection strategy changes, a brief overview, some filtration strategies, and then I wanted to review preparation steps and tools and some conclusions and recommendations. But I do want to begin by acknowledging a few key folks from Confluence Engineering: Andrew Hill, Michael Hallett, Burpee Salaziman, and Alex Mafidi. They've all been key players in helping to gather a lot of the information and research that I'll be presenting today. So beginning with background and reasons for concern. We all know change is inevitable, but it is not always good. Distribution systems hate change, and because over time, all water mains accumulate a deposit biofilm complex that we call legacy deposits. And this is really a complex of corrosion scale, biofilm, and sedimented particles that all occur together in what we call a dynamic equilibrium with the water. They can subtly adjust to minor changes in daily flows and maybe subtle changes in chemistry, but when we have larger scale changes, we can get destabilization and then release of these deposits. Now, these releases may or may not result in public health concerns, but they almost always can result in customer complaints. So what we have to remember is that we have a lot of old pipes out there, and then when we do a change, we're going to have a reequilibration process. It's during this reequilibration process that we can really start getting into some trouble. So I want to start with a pipe classification scheme. I'll be talking about some of these terminologies in the presentation, where we talk about scale forming pipe, and that's where the pipe itself can form often dense corrosion scales from interaction with the pipe material itself. This is our unlined cast, unlined ductile, steel, galvanized pipes. Compared to non-scale forming pipes, where the material that is present has either been settled or co-precipitated or adsorbed, it's not from the pipe material itself. And those are often our cement-lined, plastic, and asbestos cement pipes. The iron and manganese and biofilm that accumulate on these pipes serve as major accumulation substrates in and of themselves for other regulated metals. We commonly find these metals at varying concentrations in these pipe scales. And it's not just the big corrosion tubercles we worry about. Yes, there's a lot of iron and there's a lot of massive material, but these very thin films can be great accumulators for biofilm and these other regulated metals. When we talk about biofilm, here's the type of thing we see out there. We lovingly call these the bacon fat slides, what we can see in a free chlorine system and in a chloroaminated system. So just to provide a visual for those that don't get to look inside the pipes as often as we do. So what might be changing with a source or treatment change? Well, with new treatment, assuming it's at the same plant, and the hydraulics aren't changing, we're really looking at some chemistry changes. But with a new source integration, we have potential chemistry changes due to differences in the compatibility of the supplies, but also significant hydraulic changes that can have hydraulic scouring effects causing releases, but can also create chemistry changes because we're changing the flow dynamics in the distribution system. And of course, this is quite important because this can result in severe discolored water events, possible exposure to regulated metals, loss of customer trust, and then, of course, massive expense when we are in the reactive mode trying to solve one of these destabilization problems. So a little bit more on the types of releases. We have hydraulic and chemical releases. These are just broad categories. And if you look at the graph up here, representing a simulation of a hydraulic particle resuspension, we can see that the release events are very sporadic. They may be of shorter duration, but of high magnitude, and may not be predictable on a time scale. And then with these hydraulic releases, these particle resuspensions that often have color to them and are releasing associated iron and manganese biofilm. But then when we have a chemical release event, the time scale can be much different. It can take days, weeks, months, or even years for scales to re-equilibrate. And the release may not always be in a visible form. When we talk about even just measuring lead and copper at the tap, those are release events that you really can't see. So it's important to note that these can be happening, and we're not always having discolored water along with it. So the time and spatial components can vary significantly for a hydraulic versus a chemical release, And therefore, our monitoring approach to try to understand if these are occurring and the need to control them have to be suited to the type of release event that could be occurring. Now we have a special combo release that we lovingly call the doom loop of distribution systems, when we get simultaneous chemical and hydraulic release. And this is what we see when we're in the reactive mode to these problems. We start with an unstable chemistry condition or a change in the chemistry. We apply that to our tens or hundreds of miles or thousands of miles of distribution system pipe and premise plumbing. That creates more unstable chemistry as all those pipe reactants react with the water chemistry. And then we run out, we start opening hydrants, we start moving water, flushing, breaking off tubercles, and we damage the scales while we're trying to clean up. That exposes new fresh surfaces to have further reactions with the chemistry, and you can just see you truly can get into a doom loop. And it's this exact process that we are trying to avoid. So I want to talk about some corrosion control strategy changes that can impact water quality, starting with pH alkalinity adjustment. And one of the key takeaways here is just that you can't just match the pH of two different sources and call it good. The way the metals react to pH, DIC, oxidation reduction potential, other parameters, they're actually forming different metal species in the water. So what I've provided here is an example in the green curve of a surface water, a low alkalinity, low DIC surface water, and this is its lead solubility curve. Lead solubility is a function of pH, versus a groundwater with a higher DIC. And you can see the shapes of the curves are quite different. They behave differently at nearly all pH levels. And that's because of the different DIC, we're actually forming different lead species in the water. The groundwater is forming a lead mineral, in this case, that's dominated, it's called cerussite, and the surface water is forming a different mineral called hydrocerussite, and these have different solubility characteristics. So even if we were to say we're going to bring in a groundwater and a surface water and match the exact lead solubility level at the exact same pH, we'd still have two different lead species. And every time we alternated between those two sources, the scales have to reequilibrate. City of Tacoma Water did a, with HDR Engineering and us in support, where they harvested materials from their distribution system, brass meters, you can see here, pipe, and lead solder, actually lead goosenecks, excuse me, and operated the test rigs so that they were first all exposed to surface water at pH 8.1, and then a series of materials was harvested for visual analysis and scale analysis by University of Washington. And then the whole rig was converted over to groundwater at pH around 7.4, and another set of materials were harvested and analyzed to see the degree to which these changes were occurring. Of course, simultaneously, we were doing sampling off of the rigs to see what the lead levels were. These graphs show in blue is total lead, red is soluble or dissolved lead, so the difference between them is particulate lead. And in phase one, when we're all surface water, we can see we're hovering around, 10 micrograms per liter of lead. And then when we switched to the groundwater, we see a particulate release, much more particulate activity, and higher overall lead levels. Switch back to the surface water, a particulate release, and more particulate lead, because again, these scales are reequilibrating. And if we look at the overall solubility levels, lower in surface water, higher in groundwater, that is what the models predicted for the pH and DIC conditions of these waters. So in this case, this was very well-behaved water. It did what the models predicted in terms of lead release levels, but it's this changeover that we kept seeing, the increase in particulate levels. When we looked at some of the visual analysis and the scale analysis, you can visually see that the scales look quite different under the surface water exposure with the hydrocerussite, and there's some lead-4, this darker color. And then under the groundwater is the cerussite, and we can see the mineral structure is quite different when exposed to surface water and groundwater. So can't just match pH of a groundwater and surface water and assume that you are going to be forming the same lead species. So the goal here is to avoid alternating these sources or have a controlled blend as often as possible. Some lessons learned with orthophosphate is that once you start feeding orthophosphate, especially for lead control, you must always try to maintain an adequate residual level. Orthophosphate is forming very different lead compounds. It is not forming the carbonates. It's not forming the hydrocereosite and the cereosite. It's forming lead phosphates on the scales. The effectiveness and the dosage required are a function of the pH of the water and the DIC of the water. And characteristics that can impact your ability to maintain your target residual include calcium, iron, aluminum, and other factors. Should you stop feeding suddenly or introduce a new supply that has very different characteristics, you can imagine that you are impacting the performance of your orthophosphate. And this is really one of the major issues that happened in Flint. It was discontinuation of the orthophosphate and the whole need to try to convert to the carbonate species, which wasn't successfully done, was a major contributor to the lead release issue. So we've been learning a lot about the importance of feeding orthophosphate and maintaining orthophosphate residuals in the distribution system. I do want to briefly nod to some work that was done by Darren, Lytle, and Copeland et al. 2006 about sort of an underappreciated thing about arsenic release. Arsenic desorbs from iron as pH increases. You know, we think about arsenic treatment plants, we want to do that at a lower pH to get the arsenic to sorb to the iron media. Out in the distribution systems, all the arsenic that's on the pipes may tend to desorb as we increase our pH for corrosion control. So that could be an issue in areas that have had a lot of historical arsenic loading and something to look out for. Their findings also found that orthophosphate addition did increase arsenic release because it scavenges and there's some competitive desorption across all the pH levels. So just something to think about, small systems, groundwater systems that may have had a lot of historical arsenic loading and are changing treatment for corrosion control. With regard to disinfection strategies, we have two key issues. Chlorine loss is going to lower the oxidation reduction potential of the water. We're losing our oxidant, so it's going to change the oxidation potential and drop it. That can tend to favor soluble metals release. Since we're no longer oxidizing the metals, they can go into the more soluble form and release. Of course, we're losing our oxidant against bacteria, microbial growth, so that can increase, and taste and odors can increase as a result. However, an underappreciated issue is sudden increases in chlorination. That's going to cause an oxidation reduction potential increase, which is going to precipitate some metals and cause biofilm kill and sloughing. It can increase disinfection byproducts and also create taste and odor problems. So we do have to be careful about sudden increases in disinfectant residual as well. Talk a little more about that. But with regard to maintaining residuals and trying to prevent metals release, this is especially important on unlined cast iron scales. In this work, this was a system that was evaluating the effectiveness of flushing of unlined cast iron pipe. And so these dots here, this is comparing free chlorine residual to oxidation reduction potential. In our distribution systems, the ORP is very much controlled by our disinfectant residual. And this is what we call the clean water interface. This is the good fresh water coming into the system when we can see chlorine is good and high, ORP is good and high. And then we have sites moving farther away and maybe into dead ends or pressure zone boundaries into the system where we're losing our free chlorine, and we can see, especially in these green bars against unlined cast iron pipe, we lose the chlorine, we start releasing iron, it chews up any remaining chlorine, chews up dissolved oxygen. We can get low to negative ORPs out in the distribution system. And we see that in this graph, where now we're comparing iron to those free chlorines, and you can see the iron levels are much higher in the green squares where we had very low ORP and no chlorine, and up at our clean water interface where we have nice fresh water, there's very low iron and high chlorine. So chlorine is very important in terms of remaining, keeping iron stable on our cast iron pipes. Another sort of example of a real problem where this occurred was a pipe scale destabilization event that truly was due to an ORP plunge after a source change. This system was on surface water for decades, 60, 70 years, and this is what their unlined cast iron pipes look like. They were heavily corroded, but you can see the color of the material and the size of the tubercles. We called these chocolate chip cookies. That was the size of them. They could fit in the palm of your hand. There's a nice tan color. After they introduced a new source of supply from alternate side of the distribution system, this area became stagnant. The water mounded up in this area, became stagnant, and they lost their chlorine residual, and it literally dissolved the iron scale off the pipe. And this is now what the tubercles and the materials that were flushed out looked like coming out of the distribution system. And this occurred over miles and miles of pipe. This is what happened at the tap. This discolored water coming out of the tap, the ice trays. These are community activists that would go around following the flushing crews and scoop up all the material that was flushed out of the pipes and accumulated on the streets and bring bucket loads of this material to the city council meetings. It was very contentious and difficult, and it was determined that this was all due to hydraulic mounding and complete loss of residual, negative oxidation reduction potential, and this was reversible once it got auto flushers, kept the water moving, gently flushed the pipes, not breaking up the tubercles even more, and eventually they did have to do some main replacement. These were old, corroded main and needed some service. An example of the other direction of increasing chlorine. We're going from an unchlorinated wells to chlorinated wells, or areas that historically have consistently had low chlorine, and all of a sudden you do a change, add booster disinfection to try to solve that, and you rapidly increase the chlorine. The types of problems we see, as I've mentioned, are precipitation of particles, such as iron and manganese, that causes co-release of those regulated metals, change in the biofilm, and a quirk with copper behaves different than lead. When you're in low chlorine forms less soluble copper species, and as you add chlorine, you create more soluble copper species. So during that reequilibration phase, you may see an increase in copper release. An example of where we saw a problem with manganese, here's a system. This was fairly new pipe, only about 5 years old, but it had been receiving groundwater with non-detect levels of iron and manganese, but clearly enough in this case to be microbially adhered and absorbed to the pipe in this very slippery slime surface. And then when a surface water was introduced and high chlorine, the chlorine went from less than 0.2, 1 typical in this area to up to 0.8 all of a sudden, destabilized this material, and flushing, even coming back after 2 weeks, after 5 weeks, this tea-colored material from this ongoing destabilization of the pipe materials from the chlorine was occurring, and flushing was just not enough to get it out. Eventually I had to do swabbing 10 months later, and this is still the amount of material that was coming off of pipes that looked like this, with very thin films. So in this case, there was a widespread recurring discoloration episode that lasted for about 12 months. So this is a chemical restabilization. And that was attributed to destabilization of the legacy manganese and biofilm adhered to this pipe due to the introduction, a major increase in chlorine. So with filtration changes, I just want to talk about a couple of things. Don't have a whole lot of time to cover these in detail, but we just have to be aware that when we, in our filter plants, when we're changing coagulants, we can make changes in the chloride sulfite mass ratio, which can impact galvanic corrosion. And if we're increasing chloride levels, we also have to understand that that's not good for iron scales either. It can impact the solubility of iron. And then also aluminum breakthrough and accumulation. I want to mention that if we don't have good control of our alum, it can accumulate in the distribution system. It can exert a phosphate demand. It can create milky aluminum phosphate water out in the distribution system. It affects pipe friction, all kinds. It can accumulate lead. So definitely want to think about our control of aluminum before and during, after any treatment changes. Key objective of filtration is removal of natural organic matter. Just want to point out that impacts of NOM on metals are not straightforward, but overall good to remove. There's some research suggesting that NOM could be slightly protective for iron, and there have been mixed results for copper. But more recent research suggests that NOM itself increased solubility, pitting, and can slow the copper aging process, so it's good to remove it. NOM is generally bad for lead because it forms more soluble organic species, so again, good to remove it for metals. And we know, of course, we're removing the NOM for improved biostability and decreased disinfection byproducts. So now to talk about some preparation steps and tools utilities can use to prepare for and avoid these types of issues. I've listed 6 sort of key strategies, steps, and tools here, where first, of course, we must do a detailed assessment of the finished water and compatibility of different sources. Understand the hydraulic changes that might be occurring if you're bringing on a new source or you're adding the chemical, such as booster disinfection from a new location. How is that going to affect areas of the distribution system? Understanding what is out there on those piped materials and deposits. Reviewing your O&M strategies and capabilities. Do you have a flushing program? How do you control water age? Do you turn over reservoirs? What are your capabilities? How much would it take to enhance those capabilities? And then you can identify and prioritize the risks and develop and implement a risk mitigation strand well in advance of making these changes. I've listed a whole series of tools here under every one of these that can be used. And of course, there are varying levels of expense and complexity, but at a minimum, every system should do the monitoring and desktop evaluation, should do some flushing to see what comes out of the pipes if you can try to understand what's there, and should start developing flushing tools and programs and get going on monitoring and communication. So there's key elements that must occur no matter the system size. With regard to main cleaning and flushing as a tool, we've been learning a lot about that what comes out during flushing is really only a fraction of the story. It's what we call the hydraulically mobile fraction. And of course, that makes sense. You're applying a shear. There's a certain amount of material that's going to respond to that shear and be hydraulically mobile. And here's some photos of what came out during a flushing profile on a flush of C900 pipe at 6 feet per second. And then on that exact same stretch of pipe, doing some swabbing, passing these foam swabs where you have to have a launching station and retrieval stations. You've got a hydrant and you can launch the swabs through. And they act like a squeegee, literally. And you can see the amount of material that still just came out just after the first swab, the first pass of a swab, after unidirectional flushing of 6 feet per second. And for this utility, a total of 4 swab passes were conducted. And what we can see here in this graph is unidirectional flushing is the clear bars. It removed only about 10 to 30% of the deposits, depending on which constituent we were looking at. We looked at arsenic, chromium, iron, manganese, total suspended solids, and ATP. Swabbing, the first pass of the swab provides substantial additional benefit to remove this material. I want to emphasize we don't necessarily recommend swabbing on a scale-forming pipe. Remember, that's with all the corrosion tubercles. This is on non-scale-forming pipe where you can safely, squeegee the pipes without damaging the pipe or the corrosion scales. If you're going to do swabbing or pigging on unlined cast iron pipe on a scale-forming pipe, you probably have to have a relining plan, a rehabilitation plan. So it's key to know, you might think you've gone out and you've cleaned your system ahead of a change because you flushed, but you've probably removed about 10% of the material. The rest is still there and able to react to the chemistry and hydraulic changes that are yet to come. Also, some interesting information on iron bacteria. We keep saying these are biofilms, biologically bound iron and manganese, and it is absolutely the case. Here are some of the results we see for iron bacteria at utilities around different states in the nation. The amount that comes out during unidirectional flushing versus swabbing is orders of magnitude greater. So if we want to get rid of the stuff, we might need more aggressive and long-term planning, more labor-intensive approaches than just UDF. Need to emphasize the importance of hydraulic modeling, what a great tool it can be to assess water quality risks of new source introduction, to help understand where water age is going to change, where stagnation may become a problem, chlorine demand decay, DBP formation, understanding flow velocities, where you currently might be susceptible to accumulation or where you might be what we can call self-cleaning because you have routine high velocities or push that stuff, that hydraulically mobile stuff through. Where you're going to have flow reversals as a result of a new source introduction and where scouring and hydraulic release risks occur. And then, of course, for source tracing, to understand areas of influence where those new sources may be, what the blend fractions are, and how can you better control those blend fractions, and where you're at most risk for compatibility chemical release issues. In that plan with the 6 steps and all the tools listed, of course, there's coupon, flow through, fill and dump, materials, rigs, all kinds of different types of setups that can be used to provide some information on relative impacts of source changes. We don't use these to predict actual outcomes because we've manipulated the system too much, whether it's harvested materials you've manipulated, fill and dump, or whether you're creating coupons. Neither exactly represent what's going to happen in the distribution system, but you can get a real feel for if you're going to have a major problem or a major change. And so we recommend planning time to conduct some of these types of studies as well. Changes that are going to be implemented, low and slow is really often the way to go. Low and slow and monitoring along the way. So if you're going to, for example, need to increase from pH 7.6 to 8.6, you might need to do this in multiple steps, allowing about 3 months, we would suggest, of an equilibration period before each change, and doing water quality parameter investigative sampling all along the way until you've reached your target, and then maintaining that target for a minimum of 3 months, ideally 6 months, prior to doing lead and copper rule compliant sampling. We've observed that copper can react fairly quickly to distribution system changes for corrosion control treatment, but lead can really take months to form the protective scales that we're looking for. So in conclusion and recommendation, I tried to summarize here the key chemical shifts that require attention, regardless if they're due to a treatment or a source change. And I've listed them by the corrosion control, disinfection, filtration, and then just overall chemistry. I've listed parameters and the potential impact. So hopefully that can be a resource for those moving forward. I would like to emphasize the importance of how industry thinking really must evolve. We don't think about doing distribution system preparation studies often enough, but they really are equivalent to any sort of a treatment pilot plant study. We would not change even a coagulant up at the plant without doing pilot studies or jar tests or something. These distribution system preparation studies are equally as important. This need to remove the legacy deposits, clean up our systems prior to making a change, or just because it's going to make everything more stable and water quality better overall, that is equivalent to removal of lead service lines. We are removing the inventory of the stuff that's creating the problems. So this should be a planned, proactive approach and taken with the same level of seriousness as we would when we think about removing lead service lines. Remember, the legacy deposits can also have regulated metals in them. We want to knock down that inventory, and that really helps us, gives a lot more leverage on chemistry control and maintaining water quality if we can get rid of that inventory of deposits. And finally, having distribution system operation and maintenance plan, equally important to a treatment plant O&M plan, which nearly every treatment plant has, but we don't have them for the distribution system. You know, how we prepare the distribution system, how we're going to respond to events, manage water age, main cleaning, avoid unnecessary alternating between sources, working across departments, critically important. So last slide here, take-home messages. Treatment and source changes have caused many major water quality disasters, some that have been captured by the media, but most not captured, but your customers have experienced them. We must spend the time, effort, and expense to properly prepare for these changes. Desktop, bench, pilot scale testing, hydraulic modeling, main cleaning, all of these tools are needed to understand and manage distribution system impacts. While I'm sure a lot of you are thinking, oh my gosh, this sounds so expensive and time consuming, yes it is, but it is less expensive and significantly beneficial to do in a planned, proactive manner with proper communications along the way compared to reacting in emergency mode. I think everyone can understand when you're reacting in emergency mode, that is years, months and years of work, plus then you have to rebuild customer trust. This requires effort across the utility departments. The tools we've listed, we need folks from water quality, engineering, operations, maintenance, and communications. Everyone needs to be involved. It's imperative to have mitigated as many of these risks as possible prior to making a change, and then to understand your remaining risks and have a plan for addressing the remainder. And there are some changes that really just can't or shouldn't be made, and others that require serious study prior to implementing. We've given a few examples here. And finally, there's just still so much to learn about the complex world of distribution systems. So we appreciate the utilities and everyone that's allowed us to study their systems and allowed us to share the results with you all today. So thank you. That's the end of my presentation. Hand it back to Mike.
All right. Thank you, Melinda. An important message that we need to keep getting out there about consequences of making changes. Our next speaker is Vicente Gomez-Alvarez. Vicente is a microbiologist with EPA's Office of Research and Development, Water Infrastructure Division in Cincinnati, Ohio. Vicente's research includes microbial ecology, including the application of genomic technology and the use of computational and bioinformatics. I think I got that right, Vicente. Correct me if I didn't. Workflow platforms for the characteristics of microbial contaminants. Vicente.
Okay, can you hear me?
Yes, we can hear you.
Okay, great. I'm sharing my webcam right now. Okay, first of all, I have to thank the organizers for the invitation to present my research study. And then, of course, I have to acknowledge my collaborator, Randy Rivera from the EPA, a part of this research study. A disclaimer, the views expressed in this presentation are those of the authors and do not necessarily represent the views of policy of the agency. The outline of this presentation is divided into 4 sections. The motivation, why are we doing this? Well, we wanted to look for new approaches to predict nitrification in drinking water system. And this approach is the use of machine learning. So what is machine learning? And what type of uses of the machine learning we use is a supervised classification. We're predicting, we try to classify these different samples into, or predicted into nitrification or stable. And the practical implications of this new technology, this new approach that we can use in order to predict for nitrification. I understand that we have a diverse audience here, and I appreciate that you came here to watch my presentation. So I'm going to start with some basic terminology, and then I promise that I'm not going to be too technical in this presentation so that we can understand and we can appreciate the new technology that is right now evolving into this research area, specifically more into the genomic, into the molecular area, and how we can use or able to characterize and study these microbial communities in order to understand this ecosystem. So the first term is metagenomics. So metagenomics basically involves the sequencing and application of bioinformatics to study the genetic material for environmental samples. So we took that DNA from that community and analyze that one. Myself, I'm a microbiologist, I'm a microbial ecologist, so I study that relationship between the microbes and the environment. The second term, and within the title, is machine learning. It sounds complicated, but at the end, it's only a method to analyze and process large amount of data. We like to identify patterns and make decisions with minimal human intervention. So we fit this algorithm and then try to give a response based on what we fit that machine. And we use classification, for example, which is only to assign a class label. For example, we wanted to know is nitrification, we want to know is that your environment or your distribution system is stable. And for that matter, we use what we call supervised classification, which relies on a user to define the classes. Again, stable or failure. And these data are classified into and provide the training data of each defined class. And how we do that, how we can provide that data, we provide that data as taxonomic classification. And taxonomic classification basically is the arrangement of taxa based on similarity. For the purpose of this presentation, we're going to call our species, our organisms, the microbial communities, as a taxa, different species that are part of the population. And for that matter, in order to assign this taxonomic identification, we're going to use a proxy for that. It's what we call a 16S RNA gene marker. It's basically a piece of the gene that we're able to reconstruct their microbial phylogeny. So we're able to assign them to a taxonomic ID. Like I said, I promise not to be too much technical, but if you are more interested about deep about the methodology of how we able to design this or apply this application, you can go to and able to look into our manuscript have been accepted for publication this month in Frontiers in Microbiology. So our motivation, when we pursue this research effort, we know many drinking water utilities in the United States use chloramine as disinfectant treatment in the drinking water distribution system. And many of them experience nitrification episodes, which is detrimental impact the water quality. At the same time, it's costly and it's very time consuming in many for many water utilities. And this is the most important part of our approach, is that nitrification is a microbial process. What that means that the microbes are the ones who govern or are the ones who are responsible for this process. In briefly, the ammonia in the system provides a substrate for a population called ammonia oxidizing bacteria, which produce nitrate, which can be oxidized by the second population called the nitrogen oxidizing bacteria, which oxidize to nitrate. So many water facilities and utilities adopt water quality monitoring plans to access and determine when nitrification occurring. Usually, what they incorporate some physicochemical monitor parameters. They can select all of them to able to identify this nitrification in the system. For example, they can measure levels of chlorine residual, for example, chloramine degradation. They can measure elevate nitrate concentration, or they can measure elevate or depleted free ammonium concentration, which is the source of nutrient. They can also measure increase in nitrate concentration, which means it's a nitrification occurring. They can measure low pH, or they can measure temperature in some cases, for example, in the summer, for that matter. One of the alternatives to monitoring nitrification is biomonitoring, which is the use of biological communities as indicator of the quality of the system. These biomonitors are divided into two types. There's a culture-based and there's a culture-independent. The culture-based, as implied, you use media to grow your communities. For example, you can do a HPC, heterotrophic plate count. Of course, this method needs at least more than 72 hours of incubation. Or you can go and do most probable number, MPN, and sometimes this method can take up to a month to detect that growth and able to determine if your system is in nitrification. New molecular technologies are able to detect some population of this group that are correlated or are identified in nitrification. For example, you can do qPCR, which is the amplification of the certain regions of the genome of certain populations. But the problem with this one is you cannot target multiple populations, so you're limited to certain groups, and that will also give you some few response about the nitrification in your system. So what is the rationality of using biomonitoring? So biomonitoring may reveal the potential onset of nitrification episode before sufficient levels of chemical surrogate are detected. So that's how important, because we understand, if you look into the graph in your left, this is a hypothetical scenario of a nitrification event in your system. So if you have your disinfectant residual depleted, at one time nitrate is going to be elevated, which is a symptom of nitrification. We don't know when that starts, but if you look into the green line, the communities that are responsible for nitrification, which is, as we mentioned before, they are the one. This is a microbial process, so they are the one who began to respond to that changes in the environment, and then began to activate it, and then began to produce and then to process that ammonia, that free ammonia. So that's the reason we like to use, or like to identify these bioindicators in order to monitor our environment. Once we're able to identify this one, we're able to use this one as a potential predictors for nitrification. And that represents early events of a failed system. At this moment, many utilities are able to detect nitrification once nitrification is occurring. So that means that they're not able to stop nitrification only by doing certain processes, like, for example, a chlorine burn, for example, or other type of step, but that will be already late. So we need to stop this one. We're able to predict this one by identifying these by indicators. So our approach, how are we going to identify and use these bioindicators in order to predict nitrification? So we want to explore what we call the water microbiome. The water microbiome itself is the whole community's organisms in the environment. And we're going to do that in the chloraminate drinking water distribution system simulator. I'm going to talk in a few slides later about this simulator and how we're able to manipulate this simulator and able to obtain data from this simulator. So what we did is we able to manipulate this environment between stable and failure system. And we're able to take samples from these different steps. And we see in this graph in the center. So at each operational scheme, we're able to take samples of the community here, and using the 16S RNA approach, we're able to build what we call taxonomic profiles of these bioindicators. So the graph at your right is a representation of this approach. So we take the microbial community, we sequence that, and we're able to create this taxonomic profile from a stable to failure. And with that, we're able to identify those organisms that are responsible or flourish during this different operational scheme. So what is a supervised classification, which is the method that we're using? So supervised classification relies on the user to define the classes. Again, stable versus failure that the data are classified into. So that is very simple. So we take a data, we separate between failure and stable, and feed that to the algorithm. So this is an overview of the process of supervised classification. So first, we have the source. The source will take water, bulk water, put could be biofilm, it could be any type of source water that contain those communities or contain that affected environment. Next, we're going to take the data. And the data in this case is in the form of genomic data. With that genomic data, we build our training data set based on bioindicators. We're able to identify which organisms are the ones who flourish or are depleted during the two different operational schemes of failure and stable. We feed that training set into our machine learning model, which is a supervised classification. We evaluated that training set using receiver operation curve, which is the measure of the curve, the area under the curve. Once we have that, if we are satisfied with that training set or not, we can repeat that, feeding more data. If we are satisfied with that one, then our model is ready to classify or predict our samples based on this classification model. And we test we feed that with a testing data set, which is our unknown samples. And then we evaluated that one, and we're able to predict our samples between stable and failure. So this is it's a basic kind of process, not too much complicated. So in order to evaluate our data set, we first generate a training data set. So our training data set was obtained from a drinking water distribution system simulator, which is in operation of the US EPA Test and Evaluation Facility in Cincinnati, Ohio. The reason we do this is because this simulator, we can simulate a chlorinated water system distribution system with a start time control to simulate cycles of actual daily use. At the same time, we can manipulate the system to simulate disturbance in this case. So we can push the system to nitrification, or vice versa, and that we're able to collect samples, and which is going to be very difficult to do that in a real time or in a real time distribution system. So what we do, so in every operational scheme, at every different time, we collect some bulk water. We filter that water, which is the collection of the microorganism. We extract the DNA, we sequence that DNA, and we do exploratory analysis to determine is there an evidence in the community, in difference in the community. And we can see with this ordination plot, we can see that our community, the failure, which is in the red, and the stable, the failure with nitrification and the stable, the normal operation, are different, they're separate. That means that the community or the distribution of the community and structure of the community is different. Next, what we do is to identify which organism or species are the ones who are statistically different between both communities. So in this case, we're able to identify 8 organisms, 5 in the failure system and 3 in the stable system. That means that these organisms flourish or increase in abundance in nitrification, during nitrification, while these increase during normal operation of the distribution system. Once we identify these organisms, these bioindicators, then we construct a training data set. And this training data set is basically divided in 2 groups and what we call a binary, which means a positive and negative, or stable or failure in this case. And that's what we're going to fit our model. So we try to also evaluate other type of data. We also evaluated biomass, another typical approach to determine nitrification. We can see a buildup of biomass. I mean that there's a lot of organisms that are growing in the ecosystem, in this case in the drinking water system, because there is a depletion of the residual or disinfectant residual. And also we try to compare that with the chemical, which usually is chloramine and ammonia. This is usually what we do to measure levels of nitrification. So we do that again, supervised classification. And if we look the evaluation of the training set based on genomic, which is the taxa, based on the biomass, which is ATP, for example, and the chemical one. So the area under the curve, if we have a value of 1, it's indicated an excellent classifier. So no false positive or false negative. So you can see from our area under the curve, the taxa and the chemical have a kind of similar area under the curve. So they're very good to classify our samples, our training data set. Biomass, for example, is less than 0.5, which is equivalent to a random classification of the subject. So using ATP for classify or predict nitrification is not a good alternative. So genomic and chemical, which chemicals is right now the approach, so they are very good. So now we're going to try to test that, with some data set from different drinking water systems. And for that reason, we went to the different publications, and we took the data from published papers, articles, when they studied some different chloramine systems, for example. So we have 2 types of that one. So mostly of the data that we're able to analyze or able to retrieve from the reference, the author never classified or never determined the status of the environment. So we divided that into categorized and uncategorized instance. So we have 136 categorized instances. That means that the author tells us is their sample were collected during stable or failure nitrification event, and we have more than 230 uncategorized one. So we start with the categorized one, and using our taxa-based model, we're able to classify correctly 85% of our instances. So that means that we're able to positively identify them as a nitrification or stable system. If we look in graph to the left, this is an area under the curve. And remember that we have a value of 1, that means that we have a good prediction, we have a good model. And based on using this data, if we only use chloramine, disinfectant, and ammonia, we have an area under the curve of 0.7. If we're using our taxa, we increase that prediction to 0.8. That means that we have a better predictor using our taxa. Of course, if we use chloramine, ammonia, and nitrate, which is the indicative for nitrification, we're going to get almost a value of 1. Of course, if you already detect nitrate, that means that you may have nitrification. But the reason that we have, the motivation that we what we want to accomplish with this approach is try to identify, to predict before that buildup of nitrate occur. That means that we're able to do something before that process occurring, because it's irreversible in this case. But if we're able to categorize mostly of uncategorized, we're able to identify the stability of how stable these systems are in those uncategorized instances, although we don't know the real if they're nitrification, they're stable, which is okay, and that means that our approach also is have a value to categorize or to predict these samples that we're not able, or people were not able to identify using the standard or commercial approaches right now. So what are the practical implications of this approach? So basically is that we able to report that there's the flexibility of using the microbiome as bioindicators to predict nitrification in the system. So that means that this is, we need to, of course, to validate and to get and to try to understand the system. But we see that there's kind of hope into using these microbiome communities and able to, at some probably, able to use it instead of using chemical or physical chemical parameters. Oh, and at the same time, the distributive power of the model was not influenced by geographical location. As you can see, we're using different samples from different distribution systems around the United States and also around the world. They're using also different sequencing technology, and we're able to get a high percentage of prediction. So that's also it's a positive. At the same time, bioindicators may reveal the potential set, and this is the most important, I think, motivation about this research is that we're able to predict before nitrification occurs and utilities need to spend some money into correct this problem. But then, at the same time, this method require additional validation and it's not deployable in the present form. So, but it could be developed a portable tool. And what I say that is because technology is so advancing right now, sequencing is so advancing right now, that we're able to, in a couple of years, able to have portable tools, or maybe we can able to have tools that are able to identify those specific bioindicators in the distribution system and tell the utilities or determine the utilities how your system is they going to go, or the potential of the system go to nitrification and able to do correction before that happening. So that's really all, and thank you very much for your attention.
Thank you, Vicente. Our third speaker this afternoon is Darren Lytle. Darren is an environmental engineer for the Water System Division of EPA's National Risk Management Research Laboratory in Cincinnati, Ohio, where his primary focus is research on the quality of drinking water, and in particular, drinking water distribution system, chemical issues, that a lot of which you'll hear about today. Darren.
All right, thank you, Mike. Get my screen going here. How's that look? Does it look good?
Could you switch your display settings?
Oh yeah, right. How's that?
Looks great.
Great, thank you. Okay, so I'm going to talk about one of my favorite subjects, and that's particles. Today I'm going to focus on lead, but much of what I talk about will be applicable to other particles as well that we might find, in particular in our distribution systems. Before I start, I certainly need to acknowledge that right now in our labs in Cincinnati, we have a really great team of people, engineers, scientists, materials scientists, and others that are working in distribution system issues. A lot of us are working in the area of particulates and lead. So I just wanted to acknowledge the team here. And I'll get right into kind of why do we want to understand and study particles, in particular lead particles. And And of course, lead is an issue from a health perspective, and certainly, we don't separate out when we think about lead in distribution systems. We don't think about, particulate versus soluble, where we're thinking about the total lead. And if lead is in the particulate form, we think of it as being dissolved in our stomachs, and so we're concerned about total lead. Lead particles in general can result in large and unpredictable lead spikes, and that can be a somewhat of concern. Looking for particles in water samples could tell us a little bit about the sources of lead in the distribution system, and potentially understand perhaps the mechanism or mechanisms of lead release. Treatment approaches certainly may differ from soluble lead to particulate lead, and I'm going to fall a little short on getting too much into that aspect of it. I'm hoping here to give you sort of a basics of particulate lead, and not get too deep into the treatment approaches. But certainly approaches may differ, and the presence of particles may certainly indicate the state of corrosion control, and potentially reflect the robustness of the lead scale, particularly if that's the source of the lead particles, and potentially also be a signal of some sort of underlying corrosion-related issue. So, I want to start out with some definitions, and I myself struggle with the definitions. We as a group struggle with definitions. We're kind of all over the place sometimes. We use different terms, and so I'm trying to sort of normalize that a little bit here and just give you, our sense or our feeling or how we define things, at least these days. And so I'm going to start out with just, lead 2 versus lead 4, right? So that's, we're referring to the oxidation state of lead, and we can have lead 2 particles, and we can also have lead 4 particles in the case of lead 4 oxide. Soluble or dissolved, simply, we'll define it in a second, versus particulate or particle lead. And when we talk about soluble, really, we have to cut it off somehow, and usually we look at soluble as referring to lead levels that pass a certain filter, a pre-identified filter size. Historically, that's 0.45 micron filters, but we'll talk a little bit more in a while here to certainly indicate or show you that that's really not sufficient to separate out particulate from soluble. Again, particulate lead is then therefore defined as the difference between the total lead, that's the unfiltered lead in your sample, and the soluble fraction, that is the fraction that goes through that filter that you've defined as being your cutoff for the operational definition of soluble lead. And we can have colloidal particles, and traditionally that definition is particles ranging from 1 to 100 nanometers in diameter or micron in diameter. Nanoparticles are defined as particles that are in the nanometer range of 100 to, we'll say, 1 to 100 nanometers in diameter. I want to talk about agglomeration too, because I'll refer to that a lot, and there's a nice picture of lead agglomerates next to the text here, and that refers to the joining together of colloidal or nanoparticles in some sort of larger assemblage. And oftentimes we think of that as the forces that hold that together, perhaps are often van der Waals forces of attraction. On the opposite end of that is the repulsive forces, the electrophoretic mobility, that keeps particles from staying in suspension or driving them apart and dispersing particles uniformly across the suspension. So those are some definitions for you. Sources of lead can be the lead service line, of course, could be coming from the scale and lead service lines. It could be particles could be coming from other lead sources, brasses and leaded solders, for example. Galvanized pipes, we know that lead can sorb to iron corrosion byproducts, for example, or be associated with a galvanized pipe in the first place, and come off as a particle that might have iron and lead associated with it. Or there could be other things that the lead could be associated with, sediment and other things where lead may have absorbed to surfaces or particles downstream of where the lead source is in the first place. And lead can precipitate into bulk water as well. So lead can come off, perhaps, let's say, a pipe scale, it could come off as dissolved lead, but when it hits the water, bulk water, it precipitates as some form of lead that later can be carried on into the tap and out in the consumer's water sample. So, again, some more definitions. Corrosion control, really, I think sometimes, at least technically, sometimes is defined to cover everything. But that is, corrosion control is referred to as a means of minimizing metal release from distribution system materials. That is total metal release. When I think, you know, my materials engineering friends, you know, would refer to corrosion as a process that involves electron transfer, you know, so is it corroding metal, galvanic corrosion, uniform corrosion, localized corrosion, you know, but the point is that corrosion technically, I suppose, is one way that we release lead into the water, but just to indicate there that there perhaps is a difference in some terminologies, but the point of corrosion control, though, when it comes to, you know, drinking water, is we want to minimize these types of, you know, the galvanic corrosion, for example, can be pretty significant in a source of lead release. But really, our strategies that we focus in on are to minimize the solubility of minerals that are on the pipes themselves. You know, so what we try to do, of course, is we try to adjust the water chemistry. We try to adjust the water chemistry in such a way that we form minerals on the sources of the metal that are relatively insoluble compared to what would be there if those water changes weren't made. So, for example, the orthophosphate, the point of orthophosphate addition is because we're trying to form copper or lead phosphate minerals. pH adjustment, the same thing. We're trying to increase the pH in the case of, let's say, copper to reduce the solubility of the minerals that would be forming on the surface of the pipe. And so that's one aspect of it, of course, and that's great, and that's a good goal, but there's more to it than that. Of course, you know, there's other things that get mixed into that scale, and I'm not going to get into that. That gets into a lot of other complexities, but we do need to be aware that it's just not these minerals. There are other things there, and we need to worry about them and what those elements are and how they change as we make changes to our water. But the integrity of that scale is important too. I mean, we could put lead phosphate compounds down on the scale, but if the scale is not held together very well, then those particles may not stick around. And biofilm can be important in that process too. So we need to think about, you know, is a biofilm interacting with the surface in some way, and then the stable water quality itself. So I always say, you know, distribution systems, you know, don't like change, and that's, I mean, Melinda hit that pretty well earlier, and we don't want to make changes. So all these things are important and fall into this broader category of corrosion control. But of course, my focus here and what we're talking about is minimizing particulate release, and so that's got to be an important part of it. Again, going back to the idea that we're trying to, you know, by adding things like orthophosphate, we're trying to form minerals or solids that are relatively insoluble. But if they don't stick around, if they aren't incorporated into the scale and don't hang around, then that doesn't do us a whole lot of good either. So that's part of the whole picture of what we're trying to achieve with good corrosion control. So what do we look at when we talk about particle properties? You know, well, a lot of things. You know, size is, of course, is important in the shape and morphology. Or the shape or morphology of the particles is important. What are these particles made of? What's the mineralogy? What's the charge? Are they agglomerations? Are they clustering together, or are they individual unique particles suspended in the water? These are the kinds of questions that we ask and we want to know. And I refer you to the picture here. I want you to remember this picture because I'm going to bring this back up, but this is just an example of a suspension that contains a mix of lead phosphate, the small particles, and lead carbonate, the large particles. And I'll refer back to this in a while. So just remember that for now. When we do particle analysis and particle preparation, you know, we want to do this in the field when and where possible. We prefer not to ship these samples. You know, it's not like maybe a water sample where you can get away with acidifying back in the lab. You know, I don't feel necessarily real comfortable with long-term shipping of particulate samples. So, you know, ideally we want to prepare these as close to where we're sampling and as soon as possible, because there could be artifacts as a result. Mineralogical or aging transformations, for example, can take place. The particles can agglomerate, and you can get absorption losses, I suppose, to the bottle walls. And I'm sure there are other things we need to think about too. So this is, you know, just an example of, you know, us doing some work in the field and setting up in the back of a truck after we took samples in an individual's home. These are just some examples of, you know, I'm going to talk about TEM, transmission electron microscopy, in a minute, but here's a little grid. This is really small. This really is really small. This is the grid that we prepare in the field by just putting drops of our water onto it and allowing it to dry. So defining particles, again, you know, the particle fraction, and I already sort of talked a little bit about this in our definitions. You know, slide, and that we define that as a difference between between the filtered lead and the total lead analysis. And traditionally, soluble lead has been defined as what goes through a 0.45 micron filter, but much smaller particles can be present. Historically, in our lab, we've used 0.1 or 0.2 micron filters, and now we're really using ultrafiltration filters a lot as well, because I think we really need, if we really want to understand what's going on, that's where we need to go with it. And that's not just for lead, but a lot of that work comes too from a lot of the work that's been done in manganese. I know folks have used ultrafilters for separating out manganese particles, which are known to be very small. A couple points that if you walk away with anything, these are some really good practical tips I'm going to share with you right now. And first of all, when you filter material, you've got to consider what type of filter membrane you're using, because we've done studies, and there's a reference at the bottom here to a study that we did a few years back now, and filter materials will sorb lead for sure. And so when people show me data and they say, hey, boy, we consistently get 30% particulate lead in our samples in this pilot study we're doing. It's always 30%. And I scratch my head and I say, well, what kind of filters are you using? Because that's the sign, and not necessarily always the case by any means. I mean, you certainly could have 30% consistently of particulate lead. That's not out of the question, but one of my first questions always goes to what kind of filter you're using, because that's the kind of thing that you might observe is a consistent loss in your filtrations. We recommend, based upon the study that I referenced down below, polypropylene and mixed cellulose esters as the material of choice. They didn't absorb much lead, if any at all, in our study, so that's where we go with recommendations on that. And losses can be significant, so if you're thinking or concerned, look at this paper. Here's another big practical tip. Is the caulk gun. So for those of you who've done filtrations, you're going to appreciate this one. It can be very challenging to push water through the filters, the syringe filters. Use a caulk gun. You can see a syringe filter right here. It's amazing. I know our students greatly appreciate this innovation, we'll say. But anyways, there's a tip for you on filtrations. How we do it in the field, we take our sample, or in the lab and in our studies, we take our sample. Of course, just another way of looking at this, no filter is our total lead sample, and then we pull from that either our 0.45, 0.2, or 0.1 micron syringe filter and filter that through a separate bottle. And then we use our ultrafiltration device. Our ultrafiltration filter is a 30 kilodalton, or about, we'll say about I think 10 nanometers is the equivalent kind of pore size that we found as being the definition for what the translation will say of the size. I will say that these apparatuses, of those of you who've worked with ultrafilters, you connect this up to nitrogen, and the samples push through because of the pressures and what have you. But we definitely have found that that lead will sorb, and there's not a whole lot we can do about this material. Will absorb to the filter as well as the device. So we do a preloading procedure in advance. So we sort of, presumably and we studied this, so we have some data to sort of support this, but we preload, we'll say, the surface sites with any lead that might be in a sample in advance. And if anybody's interested in that, you can follow up with me on how we go about that specifically. So let's take a look at just some practical data then, and talk about a couple of things that we've observed. This is the use of an ultrafilter and a 0.2 micron filter in the case of some precipitation experiments that we're doing in the lab. And so this is work of one of our master students, Casey Formal, and what she's doing is she's precipitating lead, and she starts with very high concentrations, and then 5, 6, 7 milligrams per liter concentration range, and then she precipitates in the presence of orthophosphate at different concentrations. And so there's a couple of practical things I want to note here. This is at pH 8 at 50 milligram per liter dissolved inorganic carbon concentration, just as for your information. But a couple of things I want to note here is that when you look at this is the total lead, right? And then in the blue is the 0.2 micron filtered lead. So that's what's coming through a 0.2 micron filter, and then the ultrafiltered lead result. So if you look at this from the first milligram per liter or so of orthophosphate, you know, there's no difference really, you know, I mean, the difference is really small, you know, between, if any at all, between the 0.2 micron filter and the ultrafilter. So you'd walk away from this saying, oh, you know, my particles are, you know, are all pretty big. They're coming out with the 0.2 micron filter, so they must be bigger than that. But if you remember back to what I asked you to remember before, that picture of the two different particle sizes, the small lead phosphate particles and the big lead carbonate particles, that's what's happening here. So if you look at the ultrafilter and you look at see what's precipitated or what's on the surface of that, you're going to find a mix of those two solids here, okay? And a reason for that, and this is important for anybody doing solubility experiments, is that the demand for orthophosphate is too great. In other words, there's too much lead and not enough orthophosphate to reach the demand or meet the demand of all the lead in the water. So what you've got, what you end up having is a mixture of lead carbonate and lead phosphate. Very important point. So you know, if you didn't fully understand that, you know, so in other words, there's no soluble phosphate coming through these filters, and that's because it's all being bound up. So you don't really start to get a handle on what's going on until you get to a concentration where you have more or you have excess orthophosphate above and beyond what's needed to precipitate out the solids. In other words, you have soluble phosphate coming through the filter, and that doesn't happen until your total phosphorus dose or phosphate dose is above 2 milligrams per liter. I hope that makes sense. But interestingly, what you see is as you increase and you shift from a mixed big carbonate particles solid and a phosphate small particle solid to a strictly now a straight lead phosphate particle that's very small, it appears as if the lead concentration through a 0.2 micron filter actually goes up. When in reality, no, it doesn't go up, because if you look at your ultrafilter, it goes way down. And so this is a perfect example of how particle size matters, because what you formed, and I'll show you some pictures later of this, is you formed small nanoparticles of lead phosphate. And so anyways, the point is the filtrations tell different stories depending on what you're looking at. But the reality of it is these are the lead phosphate solids are very, very insoluble, but they're very, very small. And so that can be important. Small particles mean a lot of surface area, means a lot of interactions or activity with things, a lot of potential mobility as well. So just sort of expanding on that, size measurements. You know, we have different ways we could take size measurements of particles. We have, for those of you familiar with zeta potential or electrophoretic mobility, you know, there's an instrument that uses dynamic light scattering approach to also size particles. And so I'm going to show you some results here from the same suspensions, but I'm going to show you the different results that you get depending on what approach you use. So this instrument here uses a laser that's shot through a particle suspension, and then it uses the distortion of the laser as the particles move through Brownian motion, and that distortion is converted to a size. So this suspension, the results 103 nanometers, right? If I look at, let's say, the scanning electron microscope, we find that the scanning electron microscope, you know, we can't quite make out the particles. It's difficult to see. There's a lot of them on the filter. It's difficult to see. But I would say that, you know, if you look close enough, and the measurement bar is here, but trust me when I tell you that, you know, okay, most of those particles are less than 100 nanometers, but that's about as good as you can get because you can't really see them very well. X-ray diffraction actually tells you something about the crystalline size. If you look at the peaks and the width of the peaks, you can get information about the size of the crystallite size. And so X-ray diffraction told us that those particles were 16 nanometers in size. Our syringe filter, ultrafilter approach tells us that 97% of the particles are between 10 nanometers and 200 nanometers. That's about the best we can do there. So we don't get specifics. And then TEM, so the TEM now is an instrument that gives us really small particles, and here they are. And we can actually take these images and we can do some graphic analysis of the imaging using imaging software, and we come up with an average size of 32 nanometers. So we go from 32 nanometers, which is actually significantly or very close, I should say, to the X-ray diffraction. We go from 32 nanometers, 103, 116. So you know, which one are you going to trust? Well, I mean, provided your instruments are calibrated properly and everything, and of course ours is. You know, I like the TEM if you have availability of that, but you know, that's just gives you a sense for what kind of differences you might see. And again, you know, there are important solids analysis tools. I've sort of jumped ahead on this one, but We have some things in our lab, of course, the ultrafilter and looking at particles as they go through different particle size filtrations, our electron microscope, which is a good down to about a micron or so in size, and it also tells you something when connected with energy dispersive spectroscopy about the elemental composition of those particles you're looking at. Transmission electron microscope, which gives you really small particles, less than 1 micron, gives you information about shape and features, and can tell you something about the elemental composition, and it has electron diffraction, so it actually can tell you something about the crystalline nature if the particles are crystalline, help you identify what they are. EDS, again, I mentioned that, but that could be connected or part of the SEM and the TEM as a standalone approach. X-ray diffraction tells you something about the crystalline nature of the particles, and it can help you also look at crystallite size. And of course, in suspension, if the particles are suspended, you can use your electrophoric mobility approach or measurement to give you something about some information about the charge and sizing of the particles as well. Particles come in all kinds of shapes and sizes. I just, wanted to show you some pretty cool images of, we've taken over the years. Lead pyrophosphate solids here look like roses or something like that. And anglesite is often found at lower pH conditions, maybe at the interface of a leaded solder joint. I showed you the lead carbonate, lead phosphate, how different in size they can be. And lead 4 oxides are actually very small as well, so to give you a sense of different size particles. So release mechanisms, it's important to understand, well, what can result in these particle releases, and certainly, water flow changes, flow and direction and velocity changes, vibrations, water hammer, these things can cause disturbances to the pipe scale and result in a slug of particle release that might last for some time after. Whereas there are also chemical or biologically induced release mechanisms, and this might be just direct water quality changes that dissolve scale components. And again, it's just not lead components. It could be any scales. It could be other things too. So for example, there could be aluminum, or there could be calcium that's incorporated into existing scales of, let's say, lead carbonates, lead phosphates, whatever it may be. But if you disturb those, you might disturb the lead that's around them, and the result, think of it as kind of the glue kind of holding things together, and if you start to dissolve these things, you could have resulting releases of particles. It could be biological associated releases as well, and again, maybe microbiology is related to local water quality changes in the scale that could result in some sloughing off, and the biofilm itself gets sloughed off, and particles could be incorporated into that. Changes in scale incorporated particle properties as well. So, making a change in water chemistry could affect the nature of the particles that are already in the scale and cause them to come off in some way. Maybe it's charge repulsion, for example. Local corrosion related water quality changes, biofilm sloughing I mentioned, and long stagnation can result in changes in local water chemistry. And I'm sure there are others that I've forgotten here. Now I wanted to sort of go over a couple of just examples of what you can learn and maybe gain from examining particles that have been suspended in these particular cases. Are just some real examples of investigations that we've been involved with, and I would highly emphasize here too, it's like everything else, it's just not about the particles. I mean, the particle piece is just one investigative tool to help you understand, when you have a problem, whether you have a problem, that kind of thing, in trying to understand things. Tying the particles back to scale analysis is really, really important. And also the water quality and water chemistry changes are important as well. And it's really tying all these pieces all together to help tell the story as to what's going on. But this is just an example focusing in on the particles themselves. These were just some samples that we collected from a community, and particles were removed from a water that really has had a long-term problem with lead release, and so these particles were removed, and so what we see here is this is under the scanning electron microscope, but what you see is a mix of stuff, and the shading really reflects the weight, I will say, the weight of the solids. So lighter colors represent heavier, like lead elements, whereas the lighter represent lighter elements. And so if we look at different areas, and what we have here are EDS. If you haven't seen these, EDS patterns associated with areas that I've got the arrows pointed to. And so what we're seeing here is that, lead particles are present in its mix of stuff, this mix of matrix, and these particles are consisting of lead, chloride, calcium, and phosphorus. And on the other hand, though, they're mixed in with these other particles. And if you look over here, there's tin, right? There's some iron in here. There's also lead, there's silica, and so there's overlap in these patterns too, I should say. It's not like it's exactly this point. There are limitations to the instrumentation, but the point being, though, is that there's a mix of stuff in here, right? And so the lead, chloride, calcium, I mean, that might be a calcium substituted pyromorphite, chloropyromorphite. That could be, that's probably what we're talking about here. So that makes some sense, but there's also other stuff. So, when I look at this kind of thing, I think to myself, okay, well, it's a mix of stuff that are just, bound together. What could be going on here? And so I think this, to me, suggests that, you've got an area within this pipe, and they do have a lot of lead tin solder. And so within this pipe, within this sample, a 1 liter sample, you're certainly hitting those lead tin solder joints. And so this likely suggests that, yeah, this is what's going on here, is that you've got some sloughing off from a region around or near a lead tin solder joint, because you're seeing the tin, you're seeing the lead, and you're also seeing some other things. And it's not out of the question that these things could be, like iron, for example, could be there from the source water, and they do have a source water iron issue as well. So looking at these things, and again, tying us back to the scale helps us understand where this stuff is coming from. And so again, it suggests that there's some sloughing off going on. And again, the pipe scale analysis, as I've emphasized, is important to tie to it. Whereas this is case study 2. And when you look at this one, in all the samples we looked at this particular location, these are relatively uniform, really small particles. And there's nothing else really there. Again, this is a contaminated water situation. This sample was very high in total lead, but soluble lead was very low. And again, we find the same kind of situation. We find lead, chloride, chlorine, chloride is what it would be, calcium and phosphorus associated with these particles. So it's the same, maybe the same calcium substituted chloropyromorphite type of a particle, but nothing else. And so what does this suggest? Well, I mean, this might suggest now something quite a bit different, that the lead is forming, we'll say maybe more so, these particles are forming more so in the bulk water or at or near the very surface of the pipe. It's not really necessarily an issue of a pipe scale falling apart, but again, or sloughing off, but rather, particles being formed in situ somewhere that are just being taken up and picked up and moved on along the water to the water sample at the tap. So again, pipe scale analysis will certainly be helpful in understanding this, but you can see the difference in, that the kinds of differences that we observe in these practical samples. So I'm gonna wrap it up there, and just some conclusions. Particles can be important, and certainly I believe are really, kind of important, more so because I don't know that we necessarily always look for the particles. We don't get small enough sometimes. So they're certainly an important form of lead in drinking water. And the presence of particles indicates, certainly an ineffective corrosion control program overall. We don't want particles forming, and we want to understand why they do and prevent that. Sample preparation is important, and there are several tools I've illustrated that can be used to analyze particles and characterize them. Particle size determination varies with method. So when we talk about particle size, we have to remember that the method sort of dictates the size too. And then lastly, examination of particles can help identify the source of lead issues and inform us on a solution. And the solution is, as I said, I didn't really touch on the solutions because it is challenging. I guess, my thinking is avoid the problem in the first place. So do your homework up front, in advance of particular, we find ourselves dealing with particle release problems after the fact oftentimes, and we don't have the, we didn't perhaps do the studies up front to identify that, boy, a lead release particulate problem could be an issue. So, I always say, let's avoid the problems in the first place. But when not, again, using the tools that we have, looking at pipe scale, looking at water quality, and tying them all together to help understand the story and strategize for solutions is where we need to, I guess, go with it. And with that, I think I have our EPA disclaimer. This is all my opinion and not the views of the EPA. And there's my contact information. I think I'll turn it back over to Mike.
Yeah, great. Thank you, Darren. An important and I guess evolving part of lead corrosion. All right, at this point, we're going to move to questions and answers. There will probably be some pauses, and that's usually just me and the organizers here trying to pick the right questions for the right folks. So let's see, and I'm going to get the questions in front of me, right? Just minimize my screen here. That didn't help. Give us a second here.
Mike, while you're sifting through those, I noticed there were quite a few questions related to Darren's presentation missing from the handouts. There's going to be an updated handout that will be sent or included in the conference materials after this session. So just so you know. Thanks.
Thank you.
Yeah, that was my fault. I'm sorry.
A lot of people want a copy of your presentation, Darren.
I know, my fault.
All right, I'm waiting. Galen, if I'm supposed to be seeing a screen, I'm not seeing it.
We are not showing a screen for this. It's just webcams. So you're set to start answering questions or asking questions.
Okay. But where am I seeing questions? That was my question.
Okay, that's located in the questions tab of your GoToWebinar panel.
All right, so I have to go find it. All right.
Can I ask
Okay.
Darren a question while you're looking?
Okay, this question I think is probably for Darren. Does scale compose of different components disintegrate at different rates?
The scale components disintegrate at different rates. Well, you know, I guess what disintegrates depends on what has been changed. You know, I look at the equilibrium. I look at the distribution system as being in equilibrium, and so let's say you've got a lead scale that's got some aluminum in it, and it's got some calcium in it, and it's got some iron in it, and so what's going to disintegrate, we'll say, or dissolve or change is going to depend on what changes in the water chemistry. So, for example, if you take away aluminum, maybe you change from an alum coagulant to an iron coagulant, just throwing that out there as an example. You know, aluminum has changed in the water, so that's what's going to that would be what I would say is, hey, that might change. So yeah, it's hard to say. You know, it really depends on what's changing in the water. You know, is what's going to dictate what's going to change in the scale.
Great, thank you. That was kind of, I didn't get through the whole question because I didn't expand it enough, but the focus was on changes in water chemistry, and you covered that. So, okay.
Yeah, and if
All
I
right.
could
Yeah,
Go ahead. Go ahead.
add to that, in my presentation, I did try to make a table of some of the key parameters: pH, DIC, calcium, you know, and how aluminum, how they might, what they might do, but focusing more on distribution system.
And just to add, I'll say, I don't know, Mike, maybe you're going to get there, but I did notice when Melinda was speaking, someone asked a question about what was DIC, and so that's dissolved inorganic carbon. So that's just like total carbonate, CO2, bicarbonate, carbonate. So measured in milligrams of carbon per liter.
Great, thank you. Yes, that's DIC is always something we need to an acronym we need to keep repeating, I guess. So
yeah, I would add to that it's something you calculate. It's
right, exactly.
you measure pH and alkalinity, and then there are lots of nice tables and charts in the EPA guidance manuals where based on your pH and alkalinity, you can look up the DIC, and then a lot of the desktop models that we use calculate that for you. But then do be careful for the units. We always show as milligrams as carbon, but sometimes it's as calcium carbonate, or and you get like numbers in the 200-300s when you really want to be down. It can be quite different. So watch out for the units.
All right, next question is going to Vicente. How can machine learning be incorporated into hydraulic modeling?
Well, like every model, you need to fit with data. And then, for example, my data, it's a simple answer. So it's yes or no. I mean, it's failure or it's stable. There are more complicated approaches and data and classification for that matter. For myself and my Moderator, we do a simple model, which is a binary model, which is 0 and 1. But I'm sure that there's machine learning approaches for different type of questions. Right, for example, it's going to be more complicated for sure. But again, it needs to be through. A study about that. So it can be incorporated. Sure. How? That's the question.
All right, I'm looking for more questions here. Give me a second.
I guess a little just follow up on the DIC while we're looking at, there was another question about is it crucial for understanding corrosivity, and yes, it is. For all the metals, when we look at their solubility and their stability, the diagrams that we create, when you see a solubility curve with the decreasing metals, or if you see a Pourbaix diagram, those are all for a specific DIC. The pH could be changing, the metal solubility could be changing, the ORP could be changing, but the graph is created for a specific DIC. So it is a very important parameter to include in our corrosivity analyses for all the metals.
I'm still looking here. I'm not seeing all the questions, Helen.
Okay. I have a question that this is easy to answer. Somebody asked about ATP. ATP is an energy molecule. They say, is ATP monitoring is leading indicator of nitrate in the distribution? I would say it's not a leading one. Some groups are trying to look for a simple way to measure disturbance in the system, and that's the way to measure biomass, but not necessarily mean that there is nitrification in your system. It means that your biomass is beginning to increase, and that due to certain or different type of disturbance. For example, you have a disinfectant residual, you have a depletion of the effector residual. That doesn't mean you're going to lead to nitrification, it can lead to other problems, pathogens, or other type of problems. But what groups are looking, companies are looking to develop some kind of simple way to measure disturbance. And ATP could be that, but not necessarily mean to lead to nitrification.
Great, thank you, Vicente. All right, this one, I think Melinda first, and Darren if he wants to follow up. Everything I've seen today has talked about orthophosphate. What are your feelings on using polyphosphate?
Well, if you're already using polyphosphate, don't stop quickly. Again, low and slow if you're going to wean off it for any reason. But polyphosphates have their role of sequestering. They're sequestering iron and manganese and trying to prevent the iron and manganese from precipitating out, and it's almost like a pass-through chemical, right? It attaches to them and hopefully passes it right through the customer's experience and does not precipitate out. But we do see some problems with polyphosphates. They can break down and revert back to orthophosphate. When they break down, they dump the stuff they were supposed to be holding, so it all accumulates in the distribution system still, or in premise plumbing, or in the dishwasher, or upon chlorination or hot water use. And of course, we've learned quite a bit about the difference between a polyphosphate sequestering agent and going to hold metal in solution can be quite detrimental for lead control. It can increase lead release, whereas the orthophosphate is trying to precipitate or react with the lead and put it back out on the scale. So, then there's blended phosphates as well, different ratios of ortho to poly, to try to achieve both objectives of sequestering iron and manganese, yet getting some corrosion control, and probably mixed success in that arena too. But I think if we're really going to get to these tiny lead levels that the industry is getting to, we're not going to be able to keep using polyphosphates. Darren?
Well, I think you covered it. I mean, the only thing I guess I would add too is that, I know I hear this a lot, and we've had some discussions about, a polyphosphate in itself isn't a polyphosphate. So I know there's a lot of folks that, go out and they change their blends, or they change their sources for, cost savings or what have you. And so I guess it's another aspect of it to think about too, is that, it may not be necessarily the same polyphosphate even, but I think everything's, we're doing some work with the polyphosphates now and on lead, and looking at the impact on lead, and certainly we've known this, but it is very detrimental. So we have to keep that in mind, and we have to be able to counter that if it's being added for any other reason.
Remember, we're using it because we are trying to do a more inexpensive and maybe less complex approach of managing iron and manganese in sources. The ideal approach is to install filtration and remove the iron and manganese at the source.
Yeah.
This is a lower cost and way less effective approach. It may reduce some customer complaints a little bit, but the stuff is still accumulating out in the distribution system. It's creating those films we showed. They're loaded with biofilm. It's not ideal.
And it kind of expand on it. Maybe Melinda has covered it. We haven't had quite the experience yet, but I know that in Ohio, there are locations where they're trying to move just to what Melinda said. Let's address the iron up front, treat it, and then the assumption is that you can, okay, I'm treating it now, I can just take my polyphosphate away, and I we don't ourselves have experience in that, but I'm like Melinda is like, whoa, wait a minute, let's hold back here and think about what that might mean, and do it slow. Certainly that will be the goal, but there's some unknowns there, I think.
Okay, I think this one is probably, I don't know, this might be for everybody to weigh in on, given what the conversation is today. To what extent does microbial corrosion impact lead leaching? I don't know who wants to start.
Darren.
Well,
Darren.
so I mean, it's not an area that we're trying to do a better job of tying the microbiology to the corrosion. There's no doubt, that biofilm is part of scale, and so folks, Abigail Cantor, for example, has done a lot of work in this area and shown that things like nitrification, for example, can definitely have an impact on corrosion. So any biological activity that changes the water chemistry, we got to think of this as what's happening locally. So you have this biofilm of some sort, bacteria associated with the scale, and we know stuff is out there. And so they're changing water chemistry locally. And, so for example, nitrifiers will lower the pH potentially locally, and that's going to be bad locally and could cause some sort of lead release. The biofilm itself could build up and slough off for one of several reasons, I suppose. We did a little bit of work, and we do have a project right now in our research program to look at what kind of biofilm is associated specifically with lead service lines. And I know the preliminary work we did, we got a student of ours, Colin White, who did some work on this, looking at what kind of microbiology was associated with lead service lines. And he found these, a lot of these strange microorganisms that were associated with, hazardous waste, acid mining strain kinds of situations where heavy metals were present. So, these things can solubilize potentially metals in themselves. So definitely there's a relationship that we need to think about, and I think it's still an area that we need to continue to research and look more closely at.
And of course, there's the issue that the biofilm is exerting a chlorine demand, which is going to lower your ORP, which may prevent you from being able to form more stable lead-4 scale. So, there's lots of complex interactions. I wasn't sure if the question was more about if there's bacteria that utilize lead. That I don't know.
Yeah, so and it kind of works both ways too, because good corrosion control means better disinfectant residual. So I know we see this in buildings a lot, where good corrosion control of copper in particular, for example, orthophosphate. We know orthophosphate corrosion control within a building definitely reduces the chlorine demand associated with the corrosion process itself, and of course that's a good thing. So it's something else to think about, I suppose.
Okay, the next one I think I will go to Melinda. Should we be just as eager to replace galvanized service lines as we are to replace lead service lines?
From an overall water quality perspective, yes. But in terms of immediate lead reduction, we got to focus on the lead service lines first. But in terms of overall water quality degradation, biofilm growth, microbial reactions, iron release, lead accumulation, taste and odor, chlorine demand, that's all happening in the galvanized too. So if I had to prioritize, I would go with lead first, but any chance you see the galvanized, and if your program can afford it, do the galvanized right alongside it.
Great, thank you, Melinda. Okay, this is kind of a multi-part question for, I think, probably for Darren. If a system would like to do scale analysis, what options do they have? Are there any research studies they could be a part of? And we hear it's very valuable but expensive. And
that's a good point. I mean, I know we push surface and scale analysis a lot, and we do because we really do feel it's important, and particularly when there's significant or important changes that may be taking place in a water system, may be the source or the treatment. And so we really do, I think the cost up front could potentially save you a lot of cost long term if you make the change and an upset happens, we'll say that becomes pretty bad. But you're right. I agree that that there are costs associated with that too, and that may be a problem. So I think Mike Schock and his team, Mike DeSantis and Jennifer Tully and others in our group are thinking a lot about this. And so we of course we have the luxury of doing all these fancy analyses in our lab, and it's great. But of course the more you do and the more detailed you get, the more the cost is. So I think we're thinking a lot about and looking at ways to kind of get some information out to people on what tiering or how you tier sampling to give you the most bang for the buck kind of thing in some sort of document perhaps. And I think they're working towards that to help people make some decisions to get the most information they can with what they can afford.
Projects we've been involved with, we've been fortunate to have university partners that have the equipment and can do it, but there are commercial labs that you can send samples. that will processing for you. So
yeah, and I think they're getting better too, for sure. I mean, Melinda, your experience has probably been that way. I mean, I think that people are getting more experience, and as more and more people come to them looking for help.
Okay, great, thanks. Let's see. I don't see. There's a question that's not complete here on phosphate residual, and I'm not sure where to go with the question. So we could maybe move to the next one.
Hey, Mike, this is Sarah. There were some questions for Melinda that came in early on. Do you want me to read those out?
Yeah, if you I'm not seeing them, so yes, please.
Sure. So Melinda, can you describe the difference between swabbing and pigging? And maybe what those terms are referring to?
yes, okay. Swabbing is using a compressible foam swab. It can be, they're like bullet shaped or squares or cylindrical, but they're compressible sponges, literally. And you would typically size to be about 2 to 4 inch diameter, larger than the pipe, so it'll put some external pressure when you launch it through a disassembled hydrant. A pig is more of a rigid, can have plastic coating. It can have bristles and brushes, and it's much more rigid, and it's going to literally take the scale, scrape the scale off the pipe. So it's just really a more aggressive technique than swabbing.
Thank you.
And then there used to be, there's ice pigging too, which is a great, we thought it was a fabulous technique. It was brought here from the UK, but my understanding is the company that was offering it in the US anymore. So I don't know, and that was great. They'd make a slurry, like literally a Slurpee, out of using your own utility water, your own finished water, freeze it into a Slurpee consistency that could then be pumped into the distribution system, and it was much more gentle. It could move around bends and diameter changes. Things with swabbing and pigging, you can't have any butterfly valves, and you really can't have diameter changes because significant. Those are solid materials, and those can get lost in the system. It can be a little tricky. But it's the ice pigging, the ice would just melt if it went down the wrong, pipe or something. But I don't know if it just proved to be too expensive for our large diameter mains out here. They're different in the UK, smaller mains, and I think it just wasn't. I'm not sure. Maybe someone can, if someone from Suez is out there, they can type in what's going on with ice pigging.
Thanks. All right, I think this next question is for Darren. What is the relationship between concentration of lead in water and the presence of particles and its importance?
I'm not sure there's necessarily a relationship. I think every situation is unique and different depending on how the lead particles were generated in the first place, the source, and water quality and other factors. So I don't think you can generalize about any specific relationships. You have to solve that or look at that in each particular case. I'm understanding that question right.
Thanks, Darren. Let's see.
Yeah, one more question here. I think probably Darren while he's on the hook here. After replacing a lead service line, are there remaining lead particles in the premise plumbing system? And what can a homeowner do to address this? Yeah,
well, that's a good plan, and certainly that is a point of issue for many in replacing lead service lines. The fact that you're going in, you're making changes, or you're disturbing the line, I should say, to remove your lead service line will disturb, and certainly you can have particles, that could roll down into the premise plumbing from the lead service line over time, could sorb to potentially, other minerals and deposits on the pipe in the house. If you have the galvanized pipe, there's big concerns there with lead sorbing too, or being involved or associated with with the iron scale that's associated with galvanized materials as well. So those disturbances, you definitely, and there's been studies and there's been people that have looked at this, and certainly you can't have particulate release. And so, most places, many places that I deal with these days and work with, if they're going out and actively removing lead service lines, people are putting in filters for some period of time to protect the homeowners from that potential particulate release that could happen as a result of that disturbance.
And point of use filters, right?
Yeah, point of use. Yeah, sorry.
There's also a lot of guidance out there. The Research Foundation that Cornwell and Richard Brown have done on flushing homes, best practices for flushing homes to remove lead particles. Of course, that has to be done carefully and purposely, so you're not actually just making things worse and spreading it around. So there's guidance out there.
Okay, this one I have is a two-part question. I'm not sure for Melinda, I think. I'm not sure you can answer the second part, but I'll give you both. Not because you don't know, but because it's a difficult question. Is orthophosphate application, if it is frequently interrupted, what problems does this cause? And there's a question about recommended residual, which might be a little hard to answer given our format here.
We're talking about scale stability so much, and the goal is to form nice, stable scales. Darren talked, they can be multi-layer and complex, and turning orthophosphate on and off, whether it's due to having some sources treated and others are blending in. You may have treated your surface water supply, but then you have a few wells that aren't treated. There's sort of the time component to that reaction. If it's just a matter of hours or days, maybe, that it's exposed to the non-phosphate. I don't know how catastrophic that would be, but it's certainly not a good idea. If you're going to go to orthophosphate, you want to treat all your sources and try to maintain a consistent residual, throughout the system. And the dose is going to be dependent on many variables. It's hard to say. I think the typical doses in the U.S. Are probably in the 2 to 3 milligram per liter range as phosphate, but as we need to get lower and lower levels, potentially on individual household levels, trying to get down to that MCLG of 0, you might need higher doses.
Great, thank you, Melinda. Well, at this point, we are almost a minute away from 4 o'clock my time. So I will say we'll close things out. Thank you, Melinda. Thank you, Darren. Thank you, Vicente. Thanks from Sarah, who is my coworker who's helping too, and the folks at Cadmus. Thank you all very much. I thought this went very well. I hope you enjoy the rest of the workshop. Thanks.
All right. Thank you, Mike.
Thank you.